probabilities related to independent and dependent events. Our first situation here, we have a situation where one event has no effect on the other event. And as a result, we call these events independent events. Our first example here looks at two independent events. One is flipping a coin and the other is rolling a six-sided die. And it asks us what's the probability of flipping a heads and then rolling a 5 in a single trial. Now, thinking about the tree diagrams we've done in the past, what this would look like is we have our coin. It has two potential outcomes, heads versus tail. And then we have our die, and our die has 6 potential outcomes. The numbers 1, 2, 3, 4, 5, 6. This tree diagram, a bit of a pain to draw. So we're going to try to look at what the results are here to see, is there a different way? Can we think of this differently to get our answer? Well, using our old way, we think about what pathway here has a head and then a 5. Well, there's this one pathway here, head and then a 5 down there. Okay, there's one pathway. So if we wanted to say the probability of getting heads and then a 5 is going to be, well, there's one pathway out of. And the total number of outcomes here, our total number of outcomes, we have 2 outcomes for the coin times 6 outcomes for the die. So my NS, total number of outcomes, 2 times 6, or 12. Then the probability of getting a head and a 5 is going to be 1 out of 12. And that's my answer to this question. Problem is, again, we don't want to have to draw this diagram. So instead, what we can think of this as 2 fractions. Now I'm going to show this. You would never actually do this in a solution. We're just going to show, where did that 12 come from? Well, the 12 was the 2 times the 6. If we think about fractions and multiplying fractions, we can split this apart. A fraction really is multiplying 1/2 times 1 out of 6. That would result in this 1 over 2 times 6. Well, if I think about that outcome, well, what is the 1/2? Well, the 1/2 was really the probability of getting a head, and the 1 out of 6 was the probability of rolling a 5. So really our answer we can get by thinking about, instead of how many pathways out of the total, we can do probability of the first times the second. So in a general rule for independent events, if I want the probability of event A and event B, well, that's the intersection. The word and, we're looking at the intersection of the two things. We want both things to occur. So I can use that notation, intersection. And what I can do instead of drawing this tree diagram is, what about just doing probability of A multiplied by the probability of event B? So in our particular example, that was probability of A was flipping a head and then rolling a 5 was the 1/6. So that's my A times B. So an alternate example here. And some of these questions you might be able to figure out just by using logic, but we can also use our formulas here. So in this example, we have Su Ling traveling to work every day. She's determined that there's a 0.7 probability she'll wait for at least one red light, 0.4 probability that she will hear her favorite song on the way to work. What's the probability she will hear her favorite song and not have to wait? So again, this word and in here means both. We want both, means intersection. If we think of a tree diagram, again, the lights are red versus green, and then she could hear her song, yes versus no. Song, yes versus no. And really what we want to know right now is, what's this pathway? What's the probability she will hear her favorite song and not have to wait? So that means this pathway of green and then yes, hearing her favorite song. Now in this case, it looks like my potential thing would be 1 out of 4 for my probability if I think of the tree diagram. However, my probability of red versus green are not equally likely. It says it's 0.7 that she's going to have to wait for a red light, which means this pathway here of red light is a different probability than a green light. So these two will always add up to a total of 100% or 1. And so if we know that a red light is 0.7, the opposite of that, the green light, would be a 0.3. So we can't actually use a tree diagram in this example. Instead, what we're going to do is think about this idea of probability of favorite song intersection with really a green light. What I'm going to do is think about that as the probability of a favorite song. These are independent events times the probability of a green light. Well, probability of favorite song is actually 0.4. And the probability of green light is 1 minus a red light. I'm just going to write that out so we have it. 0.4 times 0.3 for a total answer of 0.12 is my probability of both things occurring. In some cases, the probability of an outcome event B depends directly on the outcome event A. When this happens, the events are said to be dependent. The outcome of the first depends on the outcome of the second. And we're going to look at that in our next example. So another one of these where we have a whole bunch of information, have the tree diagram here, or sorry, the Venn diagram drawn out for you a little bit. So I'm just going to put on here, we have course functions, we have data, and then we have calculus. Put that at the bottom. So take a minute to sort of think through how you would fill it out. Again, typically filling it out, we'll look at the center first, and then we work our way out. Functions in calculus, we'd have 25 remaining. Data and functions, we have 30 remaining. Data and calculus, there would be 0. 40 are taking calculus. Well, we already used up all 40, so there's 0 people that have just calculus. Just data, we end up having 18 left over. And just functions, we end up having 10 left over. And on the outside, when we add up the totals, and note that there was 100 students to begin with, the total of all the circles adds up to 98. So there's 2 on the outside here. This question asks, what's the probability that a student is taking calculus given that they are taking functions? Well, when I say those words, given that in English means it's happening. They must be taking functions. We know the students are taking functions. So if I look at this diagram, really what I'm doing is I'm actually ignoring some of the people. I'm saying that they must be taking functions, which means if I highlight this function circle, really I'm only interested in the people in this function circle because they must be taking functions. This is that dependent event scenario. Students must be taking functions. Well, what's the probability that a student is taking calculus? We know that they must be taking functions. Well, how many students in this circle are actually also in calculus? Well, that's this right here. This section, this overlap or intersection of functions and calculus is that piece right there. So the probability of calculus given functions is, well, how many people are taking calculus? Well, there's 25 plus 15 for a total of 40 of them that are taking calculus that are also taking functions, divided by how many people in total are taking functions. Well, if I just add up the people in that green circle because I don't care about anyone else, that's 80 people. This reduces down to 1/2.